Welcome to another session that is part of the Inspiring IB Mathematics series. In this session, we will be covering functions in the graph screen for IB applications and interpretation at the standard level. Some of the features I want to highlight today include the numerical solve feature, the solving system of linear equations, the solving polynomials to find x-intercepts, and then making use of the regression features and, of course, most importantly, the graph page. There are several functions that SLAI students need to be familiar with, most importantly, the straight line, the quadratic, the cubic, the hyperbola, exponential functions, and of course our direct and inverse functions, and then of course trigonometric functions. So let's get started with one of those. I have here a typical part of an exam question. I've just cut it down to be the maths part, but it will come in a whole series of context in some way. So I have here a function. Sometimes this might be in terms of t, so it's important that we let the students know that they need to always work in x for the graph screen. So I have 3.8 sine of 15x plus 2.3, and the domain given is between 0 and 24. For AISL, we're always in degree mode, so we need to make sure that not only is our calculate page in degree, but also our graphing page in degree. So we're going to locate a few key features and do one of these types of things where we find where the height is greater than 3.5. So I'm just going to copy this and pop it into my graph screen. So I'll hit the tab button to get a shortcut to the graph entry screen. You can also use Control G, and you can also use it from the menu. So here is my function. I'm going to press enter, and we can see there's the graph there, but it's not in the right frame that we were asked for. So it goes between -10 and +10, and -6 2/3 and 6 2/3. That's the standard graphing window. We can change that standard window, and we can change it in a few ways. We can use the zoom trig. That's specifically good for going between -360 degrees and 360 degrees. But you can see that's not what we were requiring. So a better way in this case would be to use the window settings. And so I can put in from 0 to 24. I'm actually going to put in from -1 to 25. And then I can tell it a scale. So we can go in auto scale, but we can go in anything. So any amount of degrees or whatever units are appropriate. In this case, it seems to be 24 would be 24 hours. So I'm going to go in units, and then I can also change my Y values. I might just start at -3, but I need a little bit more height. So I'm going to go up to 8. And there I have my graph. So we wanted to locate the intercepts, and we can see there's a y-intercept and a couple of x-intercepts in that time. We also wanted to find the coordinates of this maximum and this minimum. And then we wanted to find when the values were greater than 3.5. So let's get started. One of the things I really try and enforce with my students is to use trace and graph trace as a first port of call to find all the interesting points. So when we go into graph trace, it will start at a point. Sometimes it'll start at the y-intercept with most graphs, but not with trigonometric functions. So let's get over to the y-intercept. And we can do that in a couple of ways. We can now move with the left and right arrows, or we can type in a value of x that we want the coordinate to be at. So if I type in just the 0, it immediately pops up with the little menu box and I can press enter and it tells me the y-intercept is at 2.3. And then I can move across using those arrow buttons. And the beautiful thing about the graph trace is that it will stop at any highlights along the way and tell you what it is. So we're at the maximum here at 6 and the y value is 6.1. And if I scoot down to here, it will tell me there's a 0 at 14.48. And I can go to the minimum at 18. And lastly, the last 0 at 21.51. But you'll notice that while I've done that, any previous values found have no longer been saved on the screen. So if they are using graph trace, they just need to make sure that they have their pen and paper with them and they can record those values. But we can also get those values, or most of them, in another way. So I'm just going to press the escape button because at the moment I'm in graph trace, but as soon as I hit escape, I'm back to just my plain graph screen and I can use menu, analyze graph. So in particular for this question, we would be interested in the zeros, the x-intercepts, the minimum and the maximum. It does not record the y-intercept. So the y-intercept we can find through graph trace or through the geometry settings, but graph trace is by far the easiest. So let's get those x-intercepts. We go to the left, that's what lower bound means. Then we go to the right and we can see we have that point listed there. I then repeat that process for analyze graph to the left and to the right, and you can see our second x-intercept, and then I can also find the coordinates of the maximum to the left and to the right, and the coordinates of the minimum. And so now all of those points will remain on the graph. Okay, so the other part of the question was to find when h of x was greater than 3.5. So what we can do is type in 3.5. So we're getting the y equals 3.5 line graphed, and we can see that it's greater between these two values. So we'd really like to find those points of intersection, and you may have noticed in the analyze graph that there was intersection. Number 4 here. Once again, you go to the left, you go to the right, and we get that coordinate. But every time we use analyze graph, we only find one thing. So we then need to repeat that to get our second value. And there we have it. And what I really like to stress to the students is, of course, we're finding when the y value is 3.5, and we can see that quite clearly in that coordinate point. So we would want the interval between this x value and this x value. All right, so let's start with a polynomial or cubic. So once again, so I missed that, there we go. We have a cubic and we'd like to determine the x-intercepts and calculate when the function equals 4. So very similar to the last question, but I'm going to show you another way that we can approach this because it's a polynomial. But first of all, you can go to menu, graph entry and function and type in the function that way. So you can use the tab, you can use Control G, and you can use the function graph entry to get that entry line up. And here it is here. Once again, not quite seeing enough of the graph, and I have a lot of empty space to the left and the right, so I might just change my window settings so that I can get that maximum in, and I might just get rid of some of this empty space on the side. So menu, window zoom, window settings. I'm going to go from -5 to 5. The lower bound was okay. I could see that minimum quite clearly, but the maximum I needed a bit more. So I'll just go up to 12 and we'll see how that looks. And that looks much more centered in my graph screen. So once again, if I use menu graph trace, you'll see for our polynomials, it will go directly to that y-intercept. So I can find the 0, the minimum, the other 0, and come back through the y-intercept to the maximum and the last 0. But you'll notice this last 0 doesn't actually say 0. So it's a nice conversation to have with the students about what this notation means and how that means that we're actually not quite exactly on 0, but very, very close, because we're moving that decimal point 12 places. So it's going to be as close to 0 as this screen can do. Okay, so we have this polynomial, 3x cubed minus 4x squared minus 5x plus 6, and we can see quite a lot on the graph screen. But as I said before, with analyze graph, we can only do one x-intercept at a time. So here's one there, and I have to keep repeating that. So it would be good if I could get all 3 up at once, and I can using a function on the calculate page. So I'm going to go to a calculate page now and go to menu, algebra, and it's in the polynomial tools, and it's just the first option, find roots of a polynomial, because of course ours will always be real roots. Ours was a cubic, so degree 3, and we can press OK. And so this creates a little template menu that we can fill in with the coefficients of the x cubed, the x squared, the x, and the constant. So in our case, that was 3, and you can use the tab to navigate through a drop-down menu anytime. So -4, tab, -5, tab, and +6, and click on the OK. So it sets up this thing called polynomial roots or polyroots, and it's with respect to x, that's the syntax. And so all we have to do is press enter, and it tells us all 3 x-intercepts at once. So it saves quite a bit of time rather than doing the analyze graph each time. I, however, stress to my students to always draw the graph first so they can get a feel for how many x-intercepts there should be. All right, so if we go back to the question, the other thing it said was to calculate when the function is equal to 4. So like before, I could use Control G, type in y equals 4 and press enter, and I could find those points of intersection using analyze graph. But polyroots work so beautifully that we get all 3 solutions at once. Why don't we adjust this cubic to solve for the graph equal to 4? So it does take a little bit of understanding on the students' parts to say, well, what I would really like, and I'm going to go up and press enter to copy that down, is now if I wanted up at, there we go, at y equals 4, then what I've done is I'm actually looking at a translation of the function, and instead of +6, if I put in +2, I get those 3 intercept points when y equals 4. So we can have a look and see how that works with analyze graph and intersection, and there is our first value. So we can see that not only does Polyroots find all these values, it always finds them in order from left to right, which is quite handy in itself. The other thing we could have used is numerical solve. So let's have a look at how that looks with numerical solve. So if I type in that equation, 3x to the power of 3 minus 4x squared minus 5x plus 6 equal to 4, comma x, because that's the syntax required for any of these, then it's going to tell me a solution. And the difference is the solution comes as a decimal as opposed to those beautiful fractions for a start, but it only tells me one solution at a time. To get the other solutions, I can go up and enter, and I can use the control equals menu to get the given symbol. And then I can put in x is greater than, and the greater thans are also on the control equals, 0 point, and I'm going to go slightly larger than 1/3 just to make sure I get past that value. And it tells me there's another value at 2. And then, of course, I can go up and edit that. I'll change that to a 0.32, and I'll change this to a less than, also on the control equals menu, and I get my third solution. So once again, in solve and analyze graph, you do them one at a time. NSolve will find the closest solution to 0 that is positive first of all. So if there are more solutions bigger than that, they then have to go greater than. But that's where having a look at the graph will actually give them a bit of a clue. They've found this solution, so they can see there's one to the right and they can see there's one to the left. But if they're looking at the graph, then you could analyze graph. Okay, let's have a look at a hyperbola now. So we want to determine the axis intercepts and state the equations of the asymptotes. So I'm just going to copy that part and open up a graph screen. I'll use the tab. And here we have the graph. This graph screen looks appropriate. I can see the X and Y intercept, and I've got the two branches of the graph, so I can see there's obviously a horizontal asymptote and a vertical asymptote. So I would always tell the students to go to graph trace, get that y-intercept first of all, move to the left and get the x-intercept. So they're well on their way to answering the questions. For the x-intercept, it's important that the students know that this is the important feature. The denominator of the fraction is the important feature that determines vertical asymptotes. And most of the students get the idea that we want to make this 0, so x has to be -2. So while I'm in graph trace, I'm going to type in -2. Notice it opened up that box again. And when I press enter, I get the fact that it's undefined at that point. But also beautifully, we get this dotted line there to say that there's no graph at that point. But for the students, it looks just like an asymptote. So we can say that x equals -2. So graph trace shows us that asymptotic behaviour for the x values. Unfortunately, it doesn't show us the same for the y values. But what we can do is have a little investigation with the students about what happens as we get closer to positive infinity or negative infinity. And we can see that both of those branches appear to be approaching the same value. Hopefully the students start to recognise after looking at a few of these that it is going to be this value here, this minus 1.9. So we could put in that line, y equals minus 1.9. There it is there. And we can see at this point that the graph appears to be below it on this side and above it on the right-hand side. But as I said, we could have a look at what happens as x approaches infinity from either side. So with graph trace, I can put in any value. So I could put in x equals 100. And we can see that it's not quite negative 1.9. It's just a fraction above it. While I've got graph trace open, let's go to 200. And once again, we can see it's still not negative 1.9. And we could go to 1000 and we can still see that it's not negative 1.9. So we can do that in both directions, because when the students look at that, they say, well, they're touching. But when we look at the values, we can see that they're actually not. So that's our asymptotic behaviour. All right, moving on to some straight lines. So there are three forms of the straight line that are important for the students to be able to work with. So the y equals mx plus c, or in some places y equals mx plus b, is our gradient and intercept method. We also have our point intercept form and our general form. So the point intercept form is really handy because if the question does not ask for a particular format of the straight line, then this is the easiest one to generate from values in a question. But for things like Voronoi diagrams, they often ask for it in this form, the ax plus by plus d equals 0. That takes a little bit of manipulation for the students and something that they need to practice with. So I have here 2 points, A and B, that have a straight line that runs through them. So I want to show you two methods that we can get the equation of that straight line. So the first one is to use our system of linear equations, LinSolve, and then the second one is to use regression. So quite often in exam questions, students are asked to generate equations that can be used to solve these types of questions. So we want that, generally speaking, is easier in the form of y equals mx plus c. So let's start off with that. So I'm going to go to menu, and it's in algebra. By the way, I'm in a calculate page now. So solve system of linear equations is available. I'll have two equations. I'm going to call these variables though, m and c. You might like to use m and b. So now I'm going to write those equations. So those points were 2.4 and 16. So I've got 16 equals 2.4m plus c. And once again, when you have a template, you can use the tab to get to the next part of the template. Negative 7.1 is equal to 3.8m plus c. And press enter, and it tells me the values of m and c. Whatever order they are in the bracket up here is the order that they appear there. So we could write the equation as y equals negative 16.5x plus 55.6. Okay, but that's not the only way we could do it. We could also have used a regression. So what I'm going to put in the first column are the x values of both coordinates. So that was 2.4 and 3.8. And then I'm going to put the y coordinates in my second list, my B list. and negative 7.1. There they are. Now I could do my regression right now, but I'm actually going to go back up to the top and I'm going to name my lists. When you choose a name for your list, you can choose very long words if you'd like X values, but in an exam, we want the students to be operating fairly quickly, but we do want more than one letter. So I usually call mine the X's, XS. And then, of course, the Y's to go with that. Press enter, and those are now variables stored in your calculator. So what I'm going to do now is the regression. So I can do that on the Listen spreadsheet page. So it's menu, statistics, stack calculations, and it's linear regression. You'll see there are two. There's the one that's for functions, and then there's the one that's specifically for statistical applications. We're going to use the functions one, the mx plus b. And it says, oh, well, is your data in list C? Well, no, it's not. It's in the X's list. And my Y values are in the Y's list. Now you'll notice there's a little apostrophe here. That's specific to the data and statistics page, listen spreadsheet page. The next thing it says is it's going to save that function to function number 1. So it'll save it to the next available function in your particular problem. And here it is here. So we can see we've got our gradient of negative 16.5 and our y-intercept of 55.6. And it tells us the form of the equation. So it looks a lot nicer than when we did the LinSolve, where we're just given two values and we have to try and remember which is which. Okay, so it's in that format, which is very nice. But that's not the only place I could do it. I'll just, just come back and I'll put in a calculate page, because I can also calculate the regression through here. In the calculate page, we obviously have many more options than we did in the statistics page. But here we have statistics and stack calculations, and that linear regression is there. I can choose my X's and I can choose my Y's. You'll notice that they no longer have the apostrophe because we're in the calculate page, and it's saying that it's going to save it to F2 now because function 1 has already been taken. And here it is here, and you get a nice layout on your calculate screen. So some students prefer to do it on the calculate page. Some people prefer to do it on the listen spreadsheet page. You get the same results no matter where you are. So we've got a graph screen. I'll use the tab to get that up. So I can go up and have a look, and then I can go over here and say, yes, please graph that. Or if I go back to F3, I could just say, could you graph F1 of X or F2 of X, because they're the same, and there it is there. Okay, so obviously we can't see that y-intercept, but we could change our window, or if we go to graph trace, it takes us there, so we can see that y-intercept at 55.6, and if I use my right arrow, it's going to bring me back down until I get to that 0 at 3.36, and I could keep going so I can see a bit more of the screen. Anytime you change the window screen, I'll press escape, and you want to get back to your standard window screen, you can do that through window zoom and standard, and it takes you immediately back to that standard screen. So when we have straight lines in a general form, we have to be somewhat more creative to sketch these, because in press to test mode in examinations, the relation menu is not available. Also, because it's not a CAS calculator, we can't find those, rearrange the equation in terms of y. So if your students are not strong algebraically, then there are a few ways we can get around this problem and still hopefully have success for them. So I have here 2x plus 14y minus 42 equals 0. I'm going to open up a calculate page, and I'm going to use menu nsolve. So putting in that equation, 2x plus 14y minus 42 equals 0, I'd really like the x-intercept, so I'm going to solve for x. But if I do that at the moment, of course, it's not a CAS calculator, so I get an error message. But if I just add a bit more information to that. So one of the key things I drill into my students is that x-intercepts y equals 0. So let's give that condition to the calculator. So the control equals and the given y equals 0, and we get the answer of 21. I then go up and copy that and just edit that to be an x and the other one to be a y, and I get my y-intercept. So from there, the students would hopefully be able to sketch the graph. But there's still another way, which this is only available, so it's a graph screen, for straight lines. We cannot use this for other ways. So I can use my nsolve in here. Now, if you go to your menu, there's no algebra, so we're not going to get it from there, but we can type it using the keyboard. So nsolve and open up a bracket, or we can go to our catalogue. So if we go to our catalogue, now you can go into number 2 to algebra, and numerical solve is there. So I can press enter and get numerical solve. Alternatively, I can go to menu, I can go to the catalogue. Now I can go to number 1, and normally it would start at the letter A, the very first thing in the TI-nspire. But if I type the letter N through my keyboard and then scroll down, we eventually get to nsolve. Any way you get there is fine. So we then put that equation in equal to 0. And because it's the function entry, it needs to be in the form of y equals. So I put comma y. So only for the straight lines will this work. But I can do nsolve for y, and there is my straight line. And from that, I can use my graph trace to get the y-intercept. And if you scroll right across, remember it was at 21, so we need to get a little bit further along. There it is, our x-intercept at 21. So only for straight lines, but it is a nice little feature that we can do. Okay, I want to do another regression. Now we can do regressions for quadratics and for cubics. We can do exponentials, all sorts of ones, but not all of them are in the right format for what is required for applications and interpretation. But the cubic is quite nice. So I've got 4 points on the cubic. Now, in an examination, they might ask for the students to write down 4 equations that can be used to solve for the coefficients A, B, C, D, etc. But sometimes the students aren't able to do that part, but using regression, they can still get the equation of the cubic function. So let's open up a lists and spreadsheet page. So that's the green. it's got the green up here. And let's put in those values. So I'm going to call them the x's, and the coordinates were, let me get them, 0, -2, 1.5, and 1 and 3. Yep. -2, 1.5. I'm pretty sure I said -3. No, just 3. Let me go back and change that. There we are. And we've got 2, -3.4, 1.325, and 37.1. And so I can do the regression over here, menu, statistics, stat calculations, and look for cubic regression. So I have my x's and my y's. Oops, haven't quite got down to the y's. Oh, no, because I didn't label that list. Rookie mistake. So I will cancel that. Okay, need to label my list. Now if I do the regression, that should work nicely. So the x's and the y's, and there it is there. But it's not that easy to read because we don't get all of it up at once. And when you look at that equation, you're not seeing all of it unless you hover over it. So this is a case where a calculate page will make that look a lot nicer. So if I go to cubic regression and I put in my x's and my y's, there it is there. And you'll notice I've particularly chose these values because we get this interesting situation with B where the students immediately go, there's a number there, -7. And then you go, but what does that e to the -13 mean? And in fact, the coefficient of B should be 0. So that's a nicer way to see all of the coefficients at once, but there is an even nicer way to see it, and that's using a data and statistics page. So if we add our variables here, x's and y's, those are the calculations that I've been doing. They've popped up, and you can see there are the points, and we can have a look at them. We can use menu, analyze graph, and regression, and we can show the cubic regression line. And what I really like about this is we get the whole function listed. We still have that awkward coefficient that needs to be discussed, but the other values are lovely. So we've got 1.8x cubed minus 4.5x plus 2. So that's a really nice way to see the regression equation. Okay. The last thing I'd like to talk about is finding the equation of a tangent. So we can do that for a graph with using a graph page, and we need to do a few steps, but we can get the actual equation of the tangent showing on the graph. So let's open up a graph page. We want x plus 1, x minus 1. So let's type that in. Keep in mind you should always put multiply signs between your brackets or any variables, just to make that nice and clear there. And we can zoom in or out if you prefer, depending on how the graph looks, but that's okay. And we want it at x equals 2. So the first step that I would get the students to do is find the coordinates of the point at x equals 2, and that's where graph trace can help us. So if I put in x equals 2, I get the coordinate 2, 6. So that would be one of the first things I would tell students to write down on their page. Then I want the gradient at that point. So I've escaped out of graph trace and I'm going to use analyze graph and dy dx. And it asks you which position would you like. Once again, you can just type in the number and it opens up the little box and it tells you the gradient is 11. Now we want that point on the graph. That's why I've recorded that there. So analyze graph, remember, will keep things on the graph for the entire time. So now I'm going to use the geometry menu within the graph menu. And we want a tangent line. So we go to the points and lines menu and down to number 8, tangent. And then you can see we're in this tangent. And because we've marked the point, we can go with our cursor and just click on the point, and here is our equation. So I'm going to escape. That stays there, which is really nice. So you can grab that and move that aside. But what we can also do, if you're very dexterous with your control and click, is you can extend that line. So in both directions. So that was by control and click, and you can extend the line. If you find that tricky, now that we've got the equation listed, 11x minus 6, what you can simply do is type in 11x minus 6 and actually get the entire, minus 16, my mistake. Let me go back to tab, go up, minus 16. There we go. And we can see that we've got that line there. The tangent line, you're not able to find a lot of things with because that's through the geometry menu on the graph screen. But if you type it in as a function, you can then find, well, the x-intercept of that, the y-intercept of that, which they hopefully would be able to read, and so on. Well, that's it for this session, and I hope you enjoy the other sessions that are available.